Hi, my name's Sebastian. I work for the NACK Center here at Penn State University, and I'll be giving the lecture today. Today's lecture is on characterization and testing of nanotechnology structures and materials. And specifically today we'll be discussing electron microscopy. The outline for today's discussion will include scanning electron microscopy, field emission scanning electron microscopy, transmission electron microscopy, and energy dispersive spectroscopy. Let's begin with scanning electron microscopy. So a scanning electron microscope, or SEM, is a microscope that produces an image by using reflected electrons. Rudimentary SEMs use thermionic tungsten emitters. And the electron beam scans the surface of an object, and a computer constructs an image from the backscattered or emitted electrons. Typically, SEMs are capable of magnifications of up to 100,000 to 300,000 times normal size, and capable of resolutions from 4 to 5 nanometers. So here is a little diagram of an SEM. Part 1, you see that this entire thing has to be housed inside of a vacuum chamber. The second element here represents the filament, the tungsten filament, which is where the electrons are emitted. The third one is a collimating lens, which is used to change the basic size of the electron beam as it comes down the column. Number 4 is the objective lens, which is used to focus the electron beam as it passes through there. It's an electromagnetic lens, so it uses a changing current and therefore a magnetic field to kind of sculpt the shape of that lens. 5 represents the scanning coils. These are what are used to raster the electron beam back and forth across a sample. 6 is a sample where the beam would finally interact. And 7 is the sample stage, which houses your sample and is used to ground the sample. So here's another diagram. At the top we see our filament. Again, that's the electron emitter. In the middle we see our electron beam. Then we see an anode, which is actually used to accelerate the electron beam. A condenser lens, which was kind of shown as a collimating lens in the last diagram. This is actually used to, it sounds opposite of the name, it's called a condenser lens, but it actually magnifies the electron beam before it's reshaped, goes through the scanning coils, that would also be the objective lens, and then finally hits the specimen above the stage. So again, electrons are generated here. They basically boil off of the filament, are accelerated further down the column. The beam kind of broadens out and then comes back together, and then one more time in the objective lens, and then here the scanning coils basically raster the beam to different parts of your sample. Then of course you need a detector. There are multiple detectors typically on an instrument, and what these do is they basically feed back to your monitor and some other control mechanisms and amplifiers, and produce a signal that gives you the display on your computer monitor. So SEM utilizes an electron gun that produces electrons, focusing elements that shape the electrons into a beam, and a focusing system that makes the electrons strike the sample within a very small 2 to 6 nanometer spot size. As far as emission sources, rudimentary SEMs utilize heated cathode emission sources that produce electrons by a process called thermionic emission. Basically, you're heating, in this case it was a tungsten tip, Much like a light bulb, when you pass a current through it, it gets hot. The light bulb we don't really use for heat, we use for the generation of photons. In a thermionic emission, it's very similar, and you are generating photons, but primarily you're generating electrons, and we're interested in those electrons, so we accelerate those along down the column. The most common and least expensive type of thermionic emitter is the tungsten tip. And more specialized SEMs, such as FESEMs, or field emission SEMs, use cold cathode emission sources that produce electrons by field emission. So, thermionic emission, in a little bit more detail, a high electric current is passed through a metal or ceramic filament. The electrons in the filament material gain thermal energy by Joule heating, and when the thermal energy is greater than the work function of the material, the electrons are emitted from the filament and condensed into a beam. So we'll draw a quick sketch of that. If you imagine a power source and a circuit with some, there's my thermionic filament. And electrons follow this path. Okay. And eventually, due to Joule heating, the electrons kind of boil off the sharpened tungsten tip, and then can be further accelerated down the column. So there are multiple filament types. There's a tungsten hairpin filament, often used because it's inexpensive, but it does have a short lifespan within hundreds of hours. It's fast heating, it's the most common, it's also the lowest resolution. But it can also be used in pore vacuum systems, which is a bonus. The lanthanum hexaboride, cerium hexaboride types of tips are relatively expensive. They do have longer lifetimes, higher brightness, smaller spot size, but they must be heated slowly to prevent damage, and they require very high vacuum. So there are pros and cons, but definitely the most common in use in SEMs is the tungsten hairpin filament. Field emission. Let's discuss how field emission is different. So what we do is we utilize a potential gradient to overcome the work function rather than thermal energy. A filament, usually LAB6, okay, or lanthanum hexaboride, is wire sharpened to a fine point with a radius on the order of 100 nanometers. It's placed then in a large electric potential gradient. The large electric field gives the electrons enough energy to overcome the material's work function and escape from the filament surface. So the way that a field emission electron gun works, which is used in a field emission scanning electron microscope, is a bit different. Instead of using thermal energy, we use a potential gradient to overcome the work function. So now, if you can imagine, we had the same setup basically, but instead of just using thermal heating or Joule heating to get these electrons out, we basically provide an electric potential. So we have this disc-shaped, and can I draw this? So this is like a disc that we cut in half so we can see the front view of it. And basically all we do is provide some type of extraction voltage here, and then we have a potential difference, and this really helps to extract these electrons. Okay, so they're experiencing this force and this potential difference, and then they're accelerated down the column. So there are multiple species that can be produced. whenever you have an electron beam interacting with your sample. These finely focused incident electrons, first of all, strike the sample with a high voltage, from 120 up to 200 keVs. So the following types of species are created once the electron beam hits the sample. We can have backscattered electrons, secondary electrons, Auger electrons, and X-rays. All different types of species created from the bombardment of just one particular species, the electrons coming off of that tip and being accelerated down the column. So there are multiple types of species, and we'll talk about these in a little bit more detail. For example, the first one we'll talk about are backscattered electrons. So these are formed when an incident electron strikes a sample and is bounced back from the sample. Elements with higher atomic numbers absorb more incident electrons, allowing fewer to be backscattered. This gives contrast to different materials in the sample. So let's make that a little bit more clear. Let's say this is our sample here, and we have different, these are the nuclei in the sample, right? And we're really concerned with the protons because the electrons won't interact with the neutrons in the nuclei of these sample atoms. And now let's say we have some incoming electrons from the electron beam. And what happens is many of these will kind of bounce off or be absorbed by the sample or be conducted away, or will cause different products to be produced. But sometimes there's this type of elastic event which produces backscattered electrons. And these are high energy electrons. They can be emitted from well below the surface, microns below the surface, and they tell us information about what type of atoms are there. Because if you imagine, if we had heavier elements with larger nuclei or more protons in the nuclei, then we would have higher energy electrons coming back and more backscattered electrons. So this provides some type of compositional contrast for us, because if you're detecting backscattered electrons, what you'll see is more backscattered electrons come from elements with greater atomic number. So in other words, if you were looking at an SEM image of backscattered electrons and you saw bright areas, those would tend to be heavier elements, and darker areas would tend to be lighter elements, or elements with lower atomic masses. Another type of species generated by SEM is secondary electrons. These are formed when an incident electron strikes a sample, ejecting an electron from the sample. Several secondary electrons can be produced from one incident electron. Secondary electrons are typically emitted by atoms close to the surface of the sample and are highly influenced by the topography of the sample. So secondary electrons are quite different. They have low energies, around 5 electron volts, and since secondary electrons have such a low energy, there's often a biased collecting cage on a detector attached so that the electron detector can attract more electrons towards it. So again, secondary electrons are quite different. And to give us an idea of that, let's draw another sketch here. We said that they tell us a lot about topography, and we'll talk about why. The reason is because of something known as the edge effect. So first of all, these are only emitted from the very near edge of a sample, right? Only a few nanometers deep. Secondly, they have very low energies. Okay. And actually, before I do that, let's draw this. Here's our sample, and here's what happens for the emission of a secondary electron. Here's a nucleus in our sample, and it's going to have some some electrons in different energy levels. So here's an electron. Here's an electron. And if you imagine an incident electron from our beam, if it would come in and strike this electron would be ejected, but it would have very low energy. So this would be our secondary electron. Okay? And notice the only way this can escape is if it's very near the surface. If the electron were struck down here, you can see it typically won't make it out, won't escape the surface. So the ones that do escape have only small energies. So the other thing I wanted to tell you is about the edge effect. So how do we get surface topography? So here's the reason why. If you imagine the electron beam coming down on all the different parts of this sample, this represents our sample. Well, the beam is only going to react with a certain interaction volume on our sample. So let's say the beam strikes here and it interacts. Actually, the beam will interact with a certain depth below the surface. Okay? And let's look at it here and here. Okay? Now, those represents different areas where the electron beam is struck. Now, if you look at the size of that volume, which is contacting the surface, you look here, pretty big, a little smaller, very small, very small, very large, very small. So because secondary electrons are only emitted from the absolute surface, a couple nanometers deep, we would see a few electrons emitted from here, many here, just a few here, many here, a couple here, and very small here. So what you see is most of the electrons are being emitted, these secondary electrons, from edges, not flat parts, but edges. Okay? So what that means is, if you were to look at an SEM image of secondary electrons, the brighter areas would represent the edges of our sample, and the darker areas would be more planar regions of our sample. So this gives us topography, and this is known as the edge effect. Again, this tells us nothing about the composition. For that to gain compositional contrast, as you saw, we look at backscattered electrons. But for topographic contrast, secondary electrons are wonderful. Another type of species generated from the interaction of our electron beam with our sample are Auger electrons. These are low-energy electrons that are emitted from the sample to achieve an energy balance after a secondary electron has been dislodged. When an incident electron causes a secondary electron to leave an atom, a vacancy is produced in an orbital very near to the nucleus. An electron from an outer shell of the atom will fall to fill the vacancy near the nucleus, creating a surplus of energy. This surplus of energy will cause an Auger electron to be released. So here's a nice little drawing of that. Let me add some color. I think it might make some more sense to us. So here comes our incoming incident electron beam. It hits an electron, which is basically knocked out of our sample, let's say, and therefore it's a secondary electron. But now we create a little hole here. So that hole is going to be filled, that vacancy is going to be filled by a higher energy electron. In this case, it's this one. So you see here it's going to fill that vacancy, and in the process we get the emission of a different type of electron, and we call that an Auger electron. And the process is called an Auger emission. So, more on Auger electrons. Since each element has a different number of orbitals, electrons, and energies, Auger electrons are specific for each atom. So, these electrons can be used to determine the elemental composition of the sample. Also, similar to secondary electrons, because these Auger electrons have very low energy levels, they can't be emitted from a depth greater than 3 nanometers. So again, right at the surface of our sample, just a few nanometers deep, we'll have these secondary electrons emitted, and also may have Auger electrons emitted, which are actually very specific, and they provide information about the atoms the elements present in our sample, due to the characteristic nature of the energy levels and the quantized states, which are different for every element having a unique atomic number. So, here's a little diagram. We're talking about Auger electron detectors, and this is the detector here is a concentric hemispherical analyzer. So we have an electron gun. This is our electron beam. It strikes a sample. Okay, we're here. And the input lens retards the ejected electrons here. The electrons enter 2 precision machined stainless steel concentric hemispheres. And then the electrons exiting the concentric path are then multiplied and detected for analysis. Okay, there's also another type of Auger electron detector called the cylindrical mirror analyzer. In this case, the electrons are emitted from the 2 samples and focused by 2 concentric cylindrical mirrors. So we have our electron gun, obviously, our sample, the Auger electrons being focused by these 2 concentric mirrors. The electrons with energies consistent with Auger electrons are captured by the detector. The other ones are reflected by an inner mirror, so they don't get to the detector because the higher energy ones are what? They're reflected by the detector. The resulting signal is enhanced by the electron multiplier and sent through an amplified circuit prior to data acquisition. So we have our electron detector here, our electron multiplier, and then finally this would take us to basically our output or our screen. Here's a brief snapshot of very rudimentary scanning electron microscope. R.J. Lee Personal Scanning Electron Microscope. Uses a tungsten wire, has a 2 to 15 kilovolt voltage range, has a typical Everhart Thornley, which is a very standard secondary electron detector, an annular or disc-shaped backscattered electron detector, has the ability to magnify from 10 to 200,000 times magnification, may have an X-ray detector for element analysis, which we'll discuss further, and then has an operating pressure of 10 to the negative 6 torr. So, next up for our discussion is field emission scanning electron microscopy. We already talked a little bit about field emission as far as electron emission and the tips, but let's talk a little bit further about this. So the FESEM, or Field Emission Scanning Electron Microscope, is similar to the SEM. It uses a rather large diameter thermionic tip, 60,000 nanometers. Okay, it's about 60 microns. The FESEM utilizes smaller emission tips with much smaller diameters. So where the SEM used tips that were around 60,000 nanometers, now FESEM, as we may have mentioned previously, has much smaller diameters in the hundreds of nanometer range. So if our beam starts smaller, it's going to give a better final resolution, because if we start with a smaller beam, we're going to end up with a smaller electron spot size, that interacts with our sample, and therefore we will get a better resolution. So the emission, we use a cold cathode as the emission source. The emitter has a negative bias of a few kilovolts. Again, this is to help draw the electrons out of that filament. A positive high voltage anode extracts the electrons from the emitter, and this eliminates the need for thermionic emission. Again, this is field emission. So here's a diagram for an FESEM. We have a field electron emission source. We have very fine image resolution, 1 to 2 nanometers, and the samples again should be conductive. Okay, we'll talk about the importance for samples to be conductive later, but for now, let's just be aware we're bombarding our sample with electrons, and then we're trying to detect electrons coming off of that surface. So if we have a buildup of electrons, okay, then our detectors will start picking up false information. They'll be detecting electrons which weren't emitted from our sample. They'll be detecting electrons which just happen to build up on the surface. And that would be incorrect information and would basically be considered background noise and would cause aberrations in our image. And it's often called discharge effects. If we look at our diagram on the left, we see everything is basically exactly the same as a typical SEM. Some major differences are obviously cold cathode and the extraction anode. Everything else is primarily the same. We have an accelerating anode, condenser lenses, an aperture, which I don't believe we mentioned before, is basically like a small disc with micron-sized holes, and that's used to basically change how much of the electron beam we allow to pass down further through the column. Then we have scanning coils, an objective lens which will focus, and then multiple detectors like a backscattered electron detector, a secondary electron detector, our sample and our stage which holds the sample and grounds it. So, there are two types of field emission sources. There's a cold cathode, actually, very sharp, kiloelectron volts charge, not heated or cooled. The electrons actually tunnel out of the tip, and the vacuum chamber must be at very low pressures, at least 10 to the negative 8 torr. To achieve this pressure, a cryopump is often used. There's also a Schottky field emission source. This has a larger tip diameter. It's heated to at least 1500 degrees Celsius, and a vacuum chamber only around 10 to the negative 5 torr is required, and this can be achieved by roughing and turbo pumps. So here's a little bit more information about the anodes in the FESEM. The extraction anode usually requires just a few kiloelectron volts to extract or tunnel the electrons from the tip, and it's going to be located just below the field emission source. The acceleration anode usually requires tens, low tens, okay, 0 to 20 kiloelectron volts applied to accelerate the electrons down through the column towards our chamber and sample. And this is located just below the extraction anode. So again, we have our tip, and you can imagine, I know, this is a bad drawing. We have our extraction, and then acceleration. Okay, so here we extract the electrons, and here we can further accelerate the electrons. Extract, accelerate. Different voltages here. A series of electromagnetic lenses condense the electron beam to the desired size. The beam must be smaller than the feature being examined. Okay, why is that important? Well, if I ask you to measure the width of a human hair with a metric ruler. If the smallest unit on the ruler is centimeters, you're going to have a lot of trouble measuring the width of a human hair, which is probably between 50 and 100 microns. So to have a high resolution image, what we always want to have is have our spot size smaller than the feature of interest. The beam must also contain a constant current density while being condensed, and typical FESEM current density is about 17,000 angstroms per centimeter squared. A little bit more about the aperture. It's going to be a metal plate with a small hole for the beam to pass through. This usually can be adjusted by the operator. It also helps to get the electron beam down to its final diameter and uniformity. So just to be clear here, what does this look like? It looks a little bit like this, literally. And we have an electron beam. Let's pretend it's fat, because remember, it's not a single file of electrons. It does have some width dimension. So here comes our electron beam, and by selecting a certain aperture, some of that beam does not continue to pass down through the column. Scanning coils. There are actually two separate scanning coils. The first one deflects the beam back and forth in a scanning or raster fashion. The second one is referred to as a stigmator coil. This helps to correct problems that may have been caused by the XY deflection of the beam. So the first one shifts the beam in the XY direction. And so the first one can shift the beam, right, in the X and Y direction. It's a little bit difficult to draw both of those planes here. But what that does is, if we looked at our sample in a top view, we can basically make our beam interact with our sample here, 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 so on and so forth. And it will raster across our entire sample. The second one, the stigmator coil, helps to just correct any problems that may have been caused by that XY deflection. And in practice, adjusting the stigmator coils can really help clean up your image, especially at higher magnifications. The objective lens is the closest part of the FESEM to the sample. It's down here at the bottom, okay, represented by this little pentagon shape. This focuses the final beam onto the sample, and the distance between the lens and the sample, called our working distance, will ultimately determine the resolution. I mean, there are other factors like spot size, beam current, and other factors, but a short working distance typically yields better resolution and a smaller or finer beam diameter. So your working distance is literally the distance between the bottom of your objective lens and your sample when your image is in focus. For electron detection again, we have secondary electron detectors, backscatter electron detectors. We also talked about Auger electron detectors. So again, secondary electrons just are emitted from the top few nanometers of our sample, and they give us topographic contrast. Backscattered electron detectors obviously detect backscattered electrons, which can be emitted from several microns deep. They give us compositional contrast, and that's great. Up next, we're going to discuss transmission electron microscopy. So we've already gone through SEM and then FESEM. Now we'll discuss TEM, transmission electron microscopy. So this is similar to SEM, But it differs. It differs because the electron beam is transmitted through the sample. So we're not looking at different things coming back from our sample. We're looking for the electron beam being transmitted through our sample, and therefore our sample must be extremely thin. So the interaction of the electrons traveling through the sample will be analyzed. This is TEM. Let's talk a little bit about the lens system. First of all, the sample thickness must be between 50 to 200 nanometers to be viewed by TEM. Otherwise, the beam simply won't penetrate the sample. An electron gun produces monochromatic electrons that are finely focused into a beam by the use of magnets or electromagnets. There are multiple electromagnetic lenses that focus the electrons into a fine beam. There's a second condenser lens in a TEM system that will determine the brightness or intensity of the beam on a sample. This is accomplished by increasing or decreasing the beam diameter that hits the sample. So by changing the beam diameter, we're changing the brightness or beam intensity. The beam then passes through an aperture, which filters electrons that are not tightly bound in the beam from traveling to the sample. As we discussed previously, the aperture blocks the outer parts of the beam, which aren't tightly bound. The first condenser lens determines the spot size or the general diameter of the beam when it finally hits the sample. So here's a little diagram. We have our source up top, first condenser lens, second condenser lens, here's our aperture. Then the beam interacts with our sample. So we saw in SEM and FESEM, our sample was at the bottom of the column. Here you see that's not the case. Below the sample, we have many other parts. We have an objective lens, objective aperture, selected area aperture, intermediate lenses, a projector lens, and then finally a main phosphorescent screen, which will basically work as our detection scheme. So there are multiple TEM generated species. What happens is the finely focused incident electrons strike the sample with a high voltage. So let's say 120 to 200 keV. After this collision with the sample, different types of species can be created. These include backscattered electrons, secondary electrons, Auger electrons, which we already discussed, but also X-rays, unscattered electrons, elastically scattered electrons, and inelastically scattered electrons. So now if you look below our sample, we see the inelastically scattered electrons, unscattered electrons, elastically scattered electrons, and these are all part of a larger group known as the transmitted electrons. So the following species are generated in any electromagnetic microscope: backscattered electrons, secondary electrons, Auger electrons, and X-rays. However, the ones that are unique to TEM, transmission electron microscopy, are the unscattered electrons, elastically scattered electrons, and inelastically scattered electrons. X-rays is a type of species that can be generated when the electron beam interacts with our sample, and we haven't discussed this yet in too much detail, so let's take a closer look. Basically, X-rays are produced when an incident electron causes a secondary electron to leave an atom. A vacancy is produced in an orbit near the nucleus. An electron then from an outer shell will fall to fill the vacancy near the nucleus, creating a surplus of energy. This sounds a lot like the production of Auger electrons. But now this surplus of energy is released as an X-ray. So emitted X-rays have unique energies associated with each specific atom, and therefore can be used to determine elemental composition of the sample. So I'll draw a real simple diagram to help you think about this. So here are my different energy levels, all right, in a quantized representative atom here. And let's say here comes an electron from our high energy incident electron beam, and it hits this electron so hard that this electron is ejected. So let me go back to red. So this electron is ejected. And if it's ejected, what does it leave behind? A hole. Okay? A vacancy. So now, if either one of the higher energy electrons decide to come in and fill that vacancy, let's say this one does, it will emit in that process an X-ray. Okay? But if this other one had filled that vacancy instead, it would emit an X-ray. And these two X-rays would be unique. Okay, they would have unique wavelengths. And the other thing to think about is these unique wavelengths would also be characteristic of this particular atom, this particular element. So what that means is X-rays coming from a sample due to this type of interaction are characteristic of the type of elements within our sample, and therefore can be used as some type of fingerprint analysis of what elements are present in our sample at a particular region of interest. Unscattered electrons. These are another type of species we see in TEM. These are incident electrons that pass through the sample or are transmitted through the sample. Typically, thinner areas yield more unscattered electrons and appear lighter than in thicker areas. That makes sense. And generally, electrons cannot be transmitted through samples thicker than 200 nanometers or 0.2 microns without significantly higher energy. So, in the case of unscattered electrons, we would see brighter areas in thinner areas of our sample because more unscattered electrons have passed through. Elastically scattered electrons are electrons that pass through the sample but change course. They change course because they're deflected by the sample, but this is an elastic process because there's no energy loss. So Bragg's law states that similar incident electrons are scattered by the same atomic spacing. So these electrons are collected and can give us stoichiometric information about our sample, as well as atomic arrangement information, and lead to things like crystal lattice structure, okay, giving us ideas about the crystal structure of our sample. So again, elastically scattered electrons pass through our sample, are deflected without energy loss, and due to scattering, can give us stoichiometric, atomic arrangement, and crystal lattice information about our sample. Inelastically scattered electrons are electrons that pass through the sample, change course, but lose some energy in the process. We can actually look at electron energy loss spectroscopy. Okay, this is interested in the amount of energy lost as the electrons are inelastically scattered. And this amount of energy loss is characteristic, again, of the element that was hit by the incident electron beam. So this is another way that we can yield compositional and bonding information from the sample. So compositional contrast, similar to the Auger and X-ray spectroscopy, but we can also achieve bonding information from looking at these inelastically scattered electrons. As far as sample preparation for transmission electron microscopy, the samples must be very thin. Usually around 100 nanometers is a good thickness. Non-conductive samples must be coated with a conductive material to prevent charging. And what I should have stated earlier was that for scanning electron microscopy and field emission, scanning electron microscopy, it's also important that your sample be quite conductive. And if it's not, for FESEM or SEM, a typical remedy is, again, to coat your sample with a thin film of conductive material such as gold or some other noble metal, and we only need a few nanometers. Here's just a little snapshot of one type of field emission TEM. This is a Joule 2010F 200 kilovolt. We have multiple condenser aperture sizes. Has a 1.9 angstrom resolution, which is obviously much higher than the 2 to 5 nanometer resolution of even the FESEM, and far smaller resolution or spot size than the regular SEM. Again, very similar components, lenses, apertures, but a quite unique type of characterization tool. Here's a picture of it. It can operate between 100 and 200 kilovolts. This uses a Schottky zirconium oxide tungsten field emitter. And again, there are 3 apertures, first condenser, second condenser, and a condenser mini lens. So you can see, a tool operator would sit in front of the tool. Just to give you an idea of size, you could, fit a desk chair in that region in the middle, and then the column might be 6 to 8 feet tall, including the height of the desk there. So last up for discussion is energy dispersive spectroscopy, which we already kind of discussed, whether we knew it or not, when we were talking about X-ray emissions. So let's take a look at this. EDS, or energy dispersive spectroscopy. So this is really X-ray spectroscopy. It's an analytical capability that can be used in conjunction with SEM or TEM techniques. This technique is also sometimes referred to as EDX or EDXA, energy dispersive X-ray analysis. Basically, you have an SEM gun providing our high energy electron beam. The beam collides with the sample, causing some of them to be knocked out of their orbits, some of the sample electrons, that is. These electron shell positions are filled by higher energy electrons, which emit characteristic X-rays in the process. It's very sensitive for low Z elements, but not so sensitive for high Z elements. By Z, we mean atomic number. So the elemental detection is typically 0.1 to 1 atomic weight percentage. Windows in the front of the detector can absorb low energy X-rays, so EDS detectors cannot detect extremely light elements such as hydrogen, helium, and lithium. So again, this technique is very sensitive for low atomic number elements, but obviously doesn't work at all for extremely low, like the 3 we mentioned, hydrogen, helium, and lithium, because they're absorbed by the glass window on the front of the detector. And also, it's not as sensitive for higher atomic number elements. But there is a wide range over which it is a very useful characterization tool for compositional contrast. The impact of the electron beam on the sample produces characteristic X-rays that can identify elemental information. The samples must be vacuum compatible again, so it may not be possible to interrogate some organic materials, especially when you think about things such as biologicals, which have lots of water and gases inside them, will be prone to outgassing when you're trying to pump down the chamber. EDS again can give quantitative results for samples that are flat and homogeneous. So you might look down at a sample and you're using your secondary electron detector and you see no contrast because it's flat. It appears to be very homogeneous. Okay, you've used your backscattered electron detector and you still don't see very much compositional contrast. But if you go to EDS, you might see very good elemental contrast. Perhaps your backscatter electron detector didn't notice it because the differing elements have very similar atomic numbers. But the relative X-ray intensity will vary also with the angle of the surface, so irregular surfaces can cause scattered X-rays. So analyzers are used to characterize the X-ray photons for their energy or wavelength and abundance, okay, to determine the elemental makeup of the area under test. In other words, when you're using EDS for analysis, you're not only getting the type of elements present in your sample, but you're also calculating abundance to determine some type of compositional ratio of one element compared to another in your sample. EDS can also be used to gather pinpoint information, or you can use it to map the elemental composition of a larger area. And a typical spot size might be 1 micron. Okay? The reason the spot size is so large is because the interaction volume is huge. In order to get X-rays to be ejected, you have to use a very high energy incident electron beam. And the higher the energy of the beam, the further it penetrates and interacts below the surface of your sample. So you get a very large interaction region, and therefore you have a lot of information or spot size, which is yielding information to your detector. EDS is inexpensive and widely available on many SEM and TEM systems, and can be used for a number of industrial applications such as aerospace, biomedical, biotechnology, electronics, pharmaceutical, and photonics. So just to point out a couple things, to reiterate some things about X-rays and EDS. First of all, I hope everybody is aware that an X-ray is part of the electromagnetic spectrum, right? So if we imagine the electromagnetic spectrum here, and we have things like gamma rays and let's say UV, and then a tiny little visible light region, and then let's say infrared, radio, micro somewhere in there, okay? And where are X-rays? X-rays, okay? They just happen to fall in a specific region of the electromagnetic spectrum. We call them X-rays. We call basically photons, we call them X-rays as long as they fall into that specific high energy region of the electromagnetic spectrum. Okay. So what does it look like if you do EDS type of detection? Well, one thing you'll get is this type of chart where you'll have something like intensity and then electron volts plotted on the y-axis. So what you're looking at is what are the energies of these X-rays being detected. And if we know this equation, right, energy is equal to Planck's constant times frequency, we know that the energies of these photons, these X-rays, is proportional to Planck's constant times their frequency. So in other words, their specific frequencies is giving us information about their specific energies. And then the intensity is how many X-rays are we getting of those specific energies. So what we'll see is different spikes or different spikes like this, and what happens is different energy spikes turn out to be characteristic of different elements. So, for example, maybe a spike here means we have carbon present in our sample, whereas a spike at a different energy means we have gold present in our sample. Okay, so the software will actually analyze the energy levels at the highest intensities and then tell you what elements are present in your sample. Another really cool thing about EDS is called element mapping. So an element map looks kind of like this. Let's say this is our sample, okay, and we have different areas on our sample. Maybe it looks kind of like this, okay. And when you looked under compositional contrast, you got a little bit of contrast. Topography, you didn't get much information. But now you do EDS as a diagnostic tool, and then you click elemental mapping. What it'll do is, since it's actually, again, scanning the electron, rastering the electron, right, across our sample and then across the sample, it's looking at each individual point, and it records the emission spectra for each individual point. So what you get when you're done is something like this. If you tell it you want carbon, you want it to paint carbon this color orange, then it'll do that for you. And everywhere where you have elemental carbon present on your sample will appear this orange color. It'll probably look kind of pixelated because the odds of having, no background noise or anything like that is very small. But you'll end up with something like this. And then if you said, let's say this is our last sample, which was carbon and gold. If you said, I want gold to be this purple color, then obviously everywhere gold was present, you would see this type of shading. So this is called an element map, and is a very powerful tool for not only compositional contrast, but actually compositional analysis, elemental analysis. It's a very powerful tool for sharing characteristic information of your work using EDS. So this concludes today's talk. Thank you for your time.